Welcome to the Explainer. Today, we're going to tackle a classic coding problem you see all the time, especially in interviews, merging two sorted arrays. Now, it sounds simple enough, but here's the kicker. You have to do it without using any extra memory. So let's break down how to solve this really clever puzzle. To really get our heads around this, let's start with a simple analogy. Imagine you've got two lines of people, and each line is already sorted by height. How would you combine them into one single perfectly sorted line? Well, you'd probably just find a new empty spot and build the line there, right? But what if there's no new spot? So here's our game plan. We'll start with the easy way. Then we'll introduce that tricky no extra space rule. After that, we'll break down the clever solution, actually visualize it happening, see what it looks like in code, and finally, talk about why this whole thing even matters. Okay, let's dive right in. First up, we're going to look at the most straightforward solution, the one that probably just popped into your head. The intuitive approach is just to create a brand new, bigger array. You copy everything from the first array into it, then everything from the second, and then you just sort that new big array. And yeah, it works perfectly. But it's kind of like finding a whole new empty room just to line up your people. It uses a lot of extra memory, and that can be a real problem. But this is the twist that makes the problem so interesting. What if you're told you absolutely cannot use any extra space? This is where we have to start thinking a little more creatively. So in computer science lingo, this is called an O of 1, or constant space constraint. All that really means is you can't just make a big new array to help yourself out. You have to solve the problem in place, working only with the two arrays you were given from the start. And that's really the heart of it, this trade-off. On one hand, you've got a solution that's super easy to think of and code up. But on the other, you have a solution that is way more memory efficient, but it definitely requires a smarter, more complex approach. So how do we actually do it? Well, the core of this clever method is a really smart comparison strategy. We're going to use a technique with two markers, or pointers, to keep track of where we are in each array. Here is the big idea. Just think about our final perfect result. We want the first array to hold all the smallest numbers, and the second array to hold all the biggest. So let's compare the largest number in the first array with the smallest number in the second. If the number in that first array is bigger, well, it's in the wrong place. It belongs over with the other large numbers, so we swap them. This is way easier to understand when you can actually see it happen. So let's walk through a step-by-step example. Okay, here are our two sorted arrays. Our goal here is to rearrange them so array A holds the four smallest numbers, which would be 1, 2, 3, and 5, and array B holds the four largest numbers, 8, 9, 10, and 13. And remember, we have to do this without creating a third array and removing all of our arrays one by one. So we start by pointing to the last element of A, which is 10, and the first element of B, which is 2. Now, since 10 is obviously greater than 2, we know that 10 is in the wrong half of our final combined set. So we do a swap. And look at that. After the first swap, the 2 has moved to array A and the 10 has moved to array B. Now, yeah, the arrays look a little messy right now, but we've done something really important. We moved a large element to the large number array. Now we just move our pointers. The pointer in A moves one step left and the pointer in B moves one step right. And we just repeat the process. Our pointers are now at 9 in array A and 3 in array B. Again, 9 is greater than 3, so we know they're in the wrong final halves. Time for another swap. We just keep doing this swap and move process until our pointers meet or cross each other. And just look what happened. Array A and array B aren't sorted internally just yet, but we've achieved something absolutely crucial. All the smaller elements are now in the first array, and all the larger elements are in the second. They are correctly partitioned. And this leads us to the final and kind of brilliant step. Since all the small elements are now in A and all the large ones are in B, all we have to do is just sort each array on its own. And there it is. This shows our final result perfectly. The two arrays are now merged as if they were one long array, with A holding the first half and B holding the second. And we did it all without a single byte of extra array memory. Pretty cool, right? So, how does this really elegant logic actually look in code? Let's take a look at a simple Python implementation of this exact algorithm. The code is actually a really direct translation of what we just walked through. First, we set up our two pointers. I starts at the very end of array A, and J starts right at the beginning of B. Then our while loop runs as long as our pointers haven't crossed. Inside that loop is our key comparison. If the element in A is bigger than the one in B, we swap them. Then we just move our pointers inward. After the loop is done, we know the arrays are partitioned correctly. Those last 2 lines are just the cleanup. We sort A, we sort B, and we have our final result. So you might be asking, why go through all this trouble? Why not just use the simple method? Well, the answer is all about efficiency, especially when your data gets really, really big. This table sums it up perfectly. The simple merge uses O of n plus m space. That just means it needs extra memory proportional to the size of both arrays combined. It's easy to write, but it's a total memory hog. Our in-place merge, on the other hand, uses O of 1 space, basically no extra memory, which makes it incredibly powerful for large datasets or for places where memory is tight, like on your phone or a small server. And that leaves us with a final thought. Being clever about memory isn't just some academic puzzle for job interviews. In a world full of massive datasets and devices with limited resources, thinking this way is an absolutely essential skill for writing software that's fast, efficient, and robust.